NEC section 392.11 addresses spacing requirements for tray cables. Specifically, it states that space tray cable installed in a single layer shall be spaced not less than 1 inch, which is 25.4 mm apart. Now let's discuss the impact on ampacity. If tray cables are not spaced according to NEC section 392.11.3, derating may be required due to the increased bundle factor. The bundle factor is a multiplier applied to the ampacity of a single cable to account for the reduced cooling when cables are bundled together. Now, regarding derating for cables smaller than 4/0 American wire gauge, the bundle factor for a single layer of spaced cables is 1.0. However, if the cables are not spaced, the bundle factor may increase to 1.12. Let's address the topic of stacking tray cables. NEC section 392.11 only specifies spacing requirements for a single layer of tray cable. It does not prohibit stacking tray cables in a tray. Considering you do not have any cables larger than 2/0 American wire gauge in the tray, you do not need to derate the cables based on the bundle factor if you do not leave space between them. However, it is generally recommended to follow NEC section 392.11.3 and provide at least 1 inch of spacing between cables for proper cooling. It is important to consult the specific ampacity tables and correction factors within the NEC to determine the appropriate conductor size and ampacity for your installation. When dealing with electrical installations, always prioritize safety and compliance with applicable codes and standards. Now let's delve deeper into ampacity and derating factors for cable installations. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of electrical current a conductor can carry continuously under specific conditions without exceeding its temperature rating. Several factors can affect the ampacity of a cable, including the conductor material, size, insulation type, installation method, and ambient temperature. The National Electrical Code, or NEC, provides tables that list the allowable ampacities for various conductors based on these factors. Derating factors are used to reduce the allowable ampacity of a conductor when certain conditions are present that can affect its ability to dissipate heat. These conditions may include high ambient temperatures, multiple conductors in a raceway or cable tray, or the presence of other heat-generating equipment. The NEC specifies derating factors for various situations, and it's essential to apply these factors correctly to ensure the safe and reliable operation of an electrical system. When installing cables and cable trays, it's crucial to consider the spacing requirements and fill limitations specified in the NEC. As mentioned earlier, NEC section 392.11.3 requires a minimum of 1 inch of spacing between cables installed in a single layer in a cable tray. This spacing allows for adequate ventilation and heat dissipation, which helps to prevent overheating and potential damage to the cables. If cables are installed in multiple layers or are bundled together without proper spacing, the heat generated by the conductors can build up, leading to a reduction in ampacity and an increased risk of insulation failure. In addition to spacing requirements, the NEC also specifies fill limitations for cable trays, which restrict the amount of cable that can be installed in a given tray. These limitations are based on the cross-sectional area of the cables and the dimensions of the tray. Exceeding the fill limitations can restrict airflow and reduce the ability of the cables to dissipate heat, which can also lead to derating and potential safety hazards. When selecting cables for installation in cable trays, it's essential to choose cables that are specifically listed and labeled for this purpose. Tray cables, often designated as TC cables, are designed to withstand the environmental conditions and mechanical stresses associated with cable tray installations. These cables typically have a rugged outer jacket that provides protection against abrasion, moisture, and sunlight. They may also have a flame-retardant insulation material that helps to prevent the spread of fire. In addition to TC cables, other types of cables such as metal-clad or MC cables and armored or AC cables may also be permitted for use in cable trays depending on the specific application and the requirements of the NEC. It's important to consult the cable manufacturer's specifications and the NEC to determine the appropriate type of cable for each installation. When installing cables and cable trays, It's also important to follow proper installation practices to ensure the long-term reliability and safety of the system. This includes using appropriate cable supports and fasteners to secure the cables to the tray, avoiding sharp bends or kinks in the cables, and properly terminating the cables at the connection points. It's also important to inspect the cable tray system regularly to ensure that it is in good condition and that there are no signs of damage or deterioration. Any damaged or deteriorated components should be repaired or replaced promptly to prevent potential safety hazards. In summary, proper cable spacing, adherence to fill limitations, and the selection of appropriate cables are crucial for ensuring the safe and reliable operation of cable tray systems. By following the requirements of the NEC and industry best practices, electrical professionals can minimize the risk of overheating, insulation failure, and other potential hazards associated with cable installations. Furthermore, understanding the principles of ampacity and directing is essential for designing and installing electrical systems that can safely and efficiently deliver power to their intended loads. By carefully considering all of the relevant factors and applying the appropriate directing factors, electrical engineers and technicians can ensure that conductors are properly sized and protected, and that the electrical system operates within its safe limits. Always consult the latest edition of the National Electrical Code and any applicable local codes or regulations for specific requirements and guidance on cable installations and electrical safety. Continuing on the topic of ampacity and directing, let's examine some specific scenarios and examples to illustrate how these principles are applied in practice. Firstly, consider a situation where multiple current-carrying conductors are installed in a single conduit or raceway. In this case, the heat generated by each conductor can affect the temperature of the other conductors, leading to a reduction in ampacity. The NEC provides adjustment factors to account for the number of current-carrying conductors in a raceway. For example, if there are 4 to 6 current-carrying conductors in a raceway, the allowable ampacity of each conductor must be reduced to 80% of its value as listed in the NEC tables. Secondly, let's consider the impact of ambient temperature on ampacity. The NEC ampacity tables are based on an ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit. If the ambient temperature is higher than this value, the ampacity of the conductor must be reduced to compensate for the increased heat. The NEC provides correction factors for various ambient temperatures. For example, if the ambient temperature is 40 degrees Celsius, which is 104 degrees Fahrenheit, the ampacity of a copper conductor with THHN insulation must be reduced to 0.91 of its value as listed in the NEC tables. Thirdly, let's discuss the effect of conductor insulation type on ampacity. Different insulation materials have different temperature ratings which affect the amount of current a conductor can carry safely. The NEC lists the allowable ampacities for various insulation types, such as THHN, THW, and XHHW. Conductors with higher temperature ratings, such as THHN and XHHW, can typically carry more current than conductors with lower temperature ratings, such as THW. However, it's important to note that the ampacity of a conductor is also affected by the termination temperature rating of the connected equipment. If the equipment is only rated for 75 degrees Celsius, the conductor must be sized based on the 75 degrees Celsius ampacity, even if the conductor insulation has a higher temperature rating. Fourthly, let's examine the impact of conductor size on ampacity. Larger conductors have a lower resistance and can therefore carry more current than smaller conductors. The NEC provides ampacity tables for various conductor sizes ranging from small gauge wires to large cables. When selecting a conductor size, it's important to consider the load requirements, the voltage drop, and the ampacity of the conductor. The conductor must be sized large enough to carry the load current without exceeding its ampacity rating and without causing excessive voltage drop. Fifthly, let's consider the use of overcurrent protection devices, such as circuit breakers and fuses to protect conductors from overloads and short circuits. Overcurrent protection devices are designed to trip or blow when the current exceeds a certain level, thereby preventing damage to the conductor and the equipment it supplies. The NEC requires that conductors be protected by overcurrent protection devices that are sized no larger than the ampacity of the conductor. This ensures that the conductor will not be overloaded or damaged in the event of a fault. In addition to the factors discussed above, there are other considerations that could affect the ampacity and rating of conductors. These include the type of load being served, the presence of harmonics, and the altitude of the installation. It's important to carefully consider all of these factors when designing and installing electrical systems to ensure that the conductors are properly sized and protected. In conclusion, ampacity and rating are essential concepts in electrical engineering and are critical for ensuring the safe and reliable operation of electrical systems. By understanding the factors that affect ampacity and by applying the appropriate rating factors, electrical professionals can design and install systems that can safely and efficiently deliver power to their intended loads. Always consult the latest edition of the National Electrical Code and any applicable local codes or regulations for specific requirements and guidance on conductor installations and electrical safety. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others from electrical hazards. If you are not qualified to perform electrical work, it's best to hire a licensed electrician to do the job.